high or someplace that's low?
19 to 31.
19 what?
To 31.
19 to 31, so I'm going to say the amplitude to go from 19 to 31 is 6, because it's twice that big, and I'm going to use 25 as my baseline. 25 is the baseline, and 6 is the height, so it's going to go from 25 plus 6, which is 31, down to 25 minus 6, which is 19. And I'm going to run this for 20 seconds. You have valves. This is what? Closed. What do you do with your valves?
They don't work.
They just work. I knew that. I just seen it you did. All right, so here I ran an experiment, the first experiment for a sine wave. Hope this works. Oh, yes! Oh my. Oh my. I bet there was a power failure briefly last night, and the variable speed drive is not working. So let me run it for another system. I forgot about it.
How about pressure?
Somebody said, how about pressure? Did I hear that?
Yeah, you heard
It's
it.
working though. It's finished, Tony.
There's no output. Which means it's not working. You said, somebody said pressure.
Yes.
Excellent, excellent suggestion, because there's something I wanted to talk to you about here. I'm going to do the same thing that I did for them. I'm just pretending I'm smart, right? Oh, I forgot to ask you what your frequency was. Who has pressure?
There's 2.
Huh?
2.
2? Really?
I've got 0.2.
Huh?
So we're also going to get 0.2 in places.
Your pressure, you have 0.2?
Yes.
I'm going to go with 0.2. I think 2 is the wrong. I'm going to close or open?
We had a temperature close.
And the other one open?
Yes, sir.
That's what this works. It worked earlier today. Somebody remind me to go fix that thing. What do we call it?
I think
Variable speed, something.
Flow. Look! This is beautiful. This is the input. This is blue. Starts at 25. That was the baseline. It goes up 6. Goes down 6. And the red is the output. Now, who has pressure? You have pressure?
Yes.
What's the lowest percent that you could find any pressure being measured?
In our range was around 35, no, 29%.
Okay, so I'm going to do this again at a higher input. Just because I want to. All right, so I do the same thing that I did before and say, oh, how sweet it is? It's going to start out at 35. I changed the baseline, so it goes up to 41, down to 29, goes up again. Look, that's 78% through, so I got it's finished, 20 seconds. So here I can measure from the bottom to the top. That's the height of the input sine over here. It ought to be 12, 29, 41. And I can measure the height of the output. Which is about 9. 9.5, let's say, down to 3.5. 9.5 minus 3.5 is how much? 6. 6 over 12 is 0.5, so the amplitude ratio for this experiment is 0.5. Now, look at this one. This one has a peak up there. And this is where you're going to have to squelch your obsessive compulsivity. Just eyeball where the peak is here. Do not take the very, very, very peak number. It's just noise. You know that in pressure. You with me, David?
Yes, sir.
Okay. Who's the obsessive compulsive, what's that word from Seinfeld? There's a word in Seinfeld. Some of you watch Seinfeld.
Yeah.
Gary Kramer.
No. What's the, yeah, but. I can't think of the word now. Anyhow. All right. Now, you want another way of looking at this?
Sure, Doctor.
You click over here, and the input is from 41 to 29, so that's delta M. And the output is from about 3 and a fraction up to about 9 and a fraction. That's delta C, this is delta M. All right. That figure has a name, I'll tell you about it in a minute. Let's do it at a higher frequency. I'm going to change the frequency to 0.4. And I don't need to run it as long because the frequency is higher, so I'm going to run it for 15 seconds. If the frequency was lower, I'd have to run it longer. You with me, Stephanie? Because I want 3 cycles, pretty good. Oh, notice there's not much phase shift here. There's not much lag between the top and the peak of the red and the peak of the blue. Isn't that interesting? Look at this. If I click over there, I'll get that figure. It's a little bit different shape now. What do you suppose that is?
Mr. Reese's loop.
This is still 41, this is still 29. This is about 10, and this is about 3, so it's a little different. It's a different number. Amplitude ratio. How about I do another one? Higher frequency yet? 0.8. I don't need to run it for very long, so let's do it 12 seconds. So I started out at 0.1 and went to, no, I started out at 0.2 frequency, then I went to 0.4, and then I went to 0.8. So I doubled it 3 times. What do you notice here?
More lag.
You can see more lag in the red compared to the blue. It's because it's lagging in here, and it's lagging in here. Lags here over there.
An output change too.
Look at that. Now, I'm going to do another one. I'm going to double it again. What do I get if I double 0.8? But I'm going to round it off to 1 significant digit. 1.6 becomes
2.
yes. Can you do that? Can you round off to one significant figure and not get too excited about it?
Not a good thing.
Well, these are fast experiments, aren't they?
Yes.
Look at that, it's already through.
Yep.
Well, almost, not as fast through. You notice anything about lag, Nicholas?
Yes.
It's even more lag, relatively speaking. Look at that. You know, before, weren't these things leaning over this way, and now they're leaning over this way?
Yes.
If they lean this way, that means the phase angle is less than 90 degrees. If they lean this way, that means the phase angle is more than 90 degrees. If they don't lean either way, it means it's exactly 90 degrees. So I've done 4 experiments. I can take the amplitude ratio and the phase angle for each of those, and I can plot those. So let me show you how we plot those. Baseline, something in the middle of your range. This is a diagram showing the same thing. Delta C over delta M. There's one. There's one that's sort of not leaning one way or the other. There's leaning off to the left. That's greater than 90 degrees. So you make a table. How do you? Is there any software you like making tables with?
Excel.
Okay. Did you say that, Ollie? Who said that? Good. So you put your frequencies from the lowest to the highest here. Put the amplitude ratio that you calculate, uncertainty in the amplitude ratio, the phase angle that you get from your graph, and the phase angle uncertainty. And then I want you to plot those on log graphs. So here's an example of what might look like. Sorry, I said log. The amplitude ratio is log, but the phase angle is semi-log. Amplitude ratio, get these data points.